With truss models, we have three really crucial assumptions in our theory, and that is that we have pin-connected members. Members only go from joint to joint in our model. So even if they physically are connected, one long straight member, say from A to F, in our model, they're only connected from one little segment, from joint to joint to joint. So this long bottom chord from A to F is really made of four separate members in our model. And at the end of those segments, everything is pin connected. The members are straight. That loads are applied only at the joints. And the implication is that we have two force members, and because they're straight, they are either pure tension or compression. So let's challenge that conclusion and, in a sense, really derive where the conclusion is going to come from. We're going to go to this member CH and pull it out. Why that one? Well, because it's one of the more complicated arrangements in the structure. Connected to the most things, has applied loads at the joints as well. And we're going to see what we get out of taking a close look at that particular one. Now, notice, for the purpose of this model, that we've got 20-foot total height and 4 foot on the little grid scale. So that really means that what we have here is a 1-to-2 type triangle where we have 20 foot there and 10 foot on horizontal. Right? So now let's not make any options here. If we pull a pin, a model would tell us that when we pull the pin in 2D, we're going to end up with two different orthogonal components. We'll call this CHX at the top and CHY at the bottom. And you'll see in just a second why it is that I have put these in those two particular directions. And then down at the other end, see, there's no other forces applied along the member. We're ignoring the self-weight of the member as insignificant compared to all the other effects. And if that's appropriate, then it becomes obvious that for horizontal equilibrium, then the force at the other end, HCX, has to be equal opposite CHX. And then likewise, the verticals have to be equal and opposite. That only tells us about the relative natures. It does tell us about what has to be true at either end. And we're going to just use then our third equation of equilibrium, such as, let's some moments about point H and see what we get. And let's take clockwise as positive. We'll have CHX times its momentum of 20 feet. It's going in the clockwise fashion, so therefore positive. And then we've got then CHY with its moment arm of 10, nothing else, so that has to be equal to 0. So therefore, CHX is equal to 10 over 20 times CHY. That's a crucial and important relationship, 10 to 20, or you could write that as 1 to 2. And I say that's a crucial and important relationship because note what has to be the case about the resultant of those two. That triangle that would form a 1 on horizontal to 2 vertical, right? That's what we're told here, right? That the y is twice as big as what the x is. That happens be in the same proportionality as what the geometric layout of that triangle was, of 10 to 20. 10 on the horizontal, 20 there. And it had to be that way. That's exactly what this equation told us. And it's a direct consequence of members loads applied on the joints. That was a crucial aspect of that. And it tells us then that ultimately, when we go look at then the net resultant effect on that member up there at joint C end, that will have a resultant CH that has to be directed along this line, straight line between those two members. And for equilibrium standpoint, then HC at the other end has to be equal and opposite, so that we end up with, in this case, pure compression, as shown here, at least symbolically. Or, of course, this could have been turned around the other way. I made an arbitrary decision about what direction these two were going. Notice that in order to have equilibrium about point H, CHX had to go in one direction, CHY had to go in the other direction. That's why I laid those out in the way that we did. We could have done that development work in the other direction, and we would have the same result. Is just that we would have ended up with then net tension ultimately instead of net compression. And for the actual loading situation in the truss that we have, that might turn out, we think, to be far more likely the case. Okay, so that's a proof of why it is that if we end up with pin-connected members, straight members, loads applied only to the joints, we have two forced members, where that really means we only have one unknown, because if we know one, we know the other end, and that we end up with either pure tension or compression. As they say in the math world, QED. Thus it has been proved.